Welcome to our computer networking project presented by Raymon, Ganaa, and Nick. The project involves two parts. A Traceroute, personalized Traceroute tool, as well as a visualizer for the topology that we create, capturing the nodes that are visited through probes sent within protocols UDP, TCP, and ICMP.
So for the arguments, we have the text file, which is the name of the text file that we have to submit with the program, and then there's -n, another variable another argument that does not resolve host names. There's W, and that's the wait time for ICMP response, which ranges from 1 to 300 seconds, and M, which is the initial TTL, which is defaulted to 1, and there's max TTL with a capital M. Basically max hop, right? Yeah. And for P, this is port that you can change if you're choosing UDP destination. UDP as your protocol. And Q, which is numbers of series per hop, which is defaulted to 1 for us, but I think for Windows and like Mac, it's 3. We just did it for 1. We just put the default as 1 to make it faster. And for protocols, you can either choose ICMP, UDP, TCP, or all of them. But as default, it runs through all of them, starting with UDP and then TCP, and finally ICMP. For data size, you can choose up to 0 to 1420, with 80 bytes going through the headers, and the MTU being 1500. And for packet delay, which is simulating lag, you can set this up by however much seconds as you want, but as default we put it as 0. And for the arguments, we just put them in the text file and then run them for every target line we have. And then here is the part where we actually run the trace route that we have talked about earlier.
So now we're going to demonstrate the Traceroute tool in action. First, we'll run the first command, Python trace4 with only text file, only one .text file containing one IP address, and we'll be using the TCP protocol with Q equals to 3, meaning we'll be sending 3 probes per hop. So here we've got immediately TCP, the trace reporting TCP 111, so there's 3 hops there, 3 probes there, TCP 222, and they're demonstrating the IP addresses as well as the latency on the right side. And this is currently at ×8 speed, and after this is done, we'll have a report, a visualizer representing the nodes that we reach at every hop. So you can see here we reach 15 hops in total, and there are some hops that are missing, and this represents missed packets, lost packets. Here we've got the visualizer. This is the first one, which shows the nodes with the IP addresses, the addresses as well as the latency between every edge, and the length of the edge represents the latency, the length of the edge, and the time is also reported there in milliseconds. And it's interactive. We can move it around to get a good understanding of the pathway that we have. Next we have the geolocation visualizer. So for every IP, every address within the city, the addresses here are overlapped, but it shows the general pathway throughout the world when requesting a trace route. So this one shows Shanghai and the Hebei province, Beijing. For our next test, we're going to use the same text file with only one IP address, but with UDP protocol specified with capital M equal to 8, meaning that there is a TTL of max TTL of 8. So as soon as we get to 8 hops, the request is timed out, but we do have a representation of the pathway that we do achieve.
Some of the requirements to use our multi-protocol traceroute tool include having Python 3.7 or newer, and also an internet connection for IP geolocation and the DNS resolution. So the step one for using our project is to install all the necessary Python libraries. Then you have to prepare the target input file that will list all of the destinations you want to reach. Then you run the program. My contributions mainly include creating the two interactive functions to visualize results. That's plot interactive graph and plot geolocation map. For plot interactive graph, it receives the information of the output from multi-protocol traceroute, and then using the network library will create an interactive graph in the form of an HTML file. The length of the edges of the path that the traceroute creates is relative to the size of the latency. And then the second function is plot geolocation map, and this is similar. It takes information from the trace multi-protocols function, and then will use the information to create a graph on a map of all the public IPs that were traveled through that.
So here we're running a third test with the default arguments, but with the text file containing 2 IP addresses. We can use a text file containing as many IP addresses as you require, but here we're using just 2 to demonstrate. And we also do not, for this test, we do not specify a protocol, UDP, ICMP, or TCP, so by default it's going to report all 3. Here we can see UDP's finished reporting. We're currently doing a TCP, and soon there will be an ICMP trace report. And this is already the visualizer for the UDP is showing nodes in the US, so this makes sense because this is for google.com. And now it's at ×8 speed, and soon we'll have the ICMP request trace coming through. In the meantime, discussing our contributions. So Ganaa's contributions were mainly the skeleton code for getting the traceroute to work, as well as the multi-traceroute protocol function to work. So by default, having a representation for the traces of all 3 protocols. My contributions were mainly the implementation and the logic behind all of the arguments. So we have whether to resolve or not resolve the addresses to host names. In fact, this is a socket. This is from the socket library, and it does take a lot of time for the output to come through. And soon we'll demonstrate with the -n, which specifies not to resolve addresses to host names, that the program runs a lot faster. There's also the wait time for the ICMP response, the initial TTL, the max TTL, the UDP, TCP destination port, -q, the number of series per hops, UTI specifying which protocol to use, by default all protocols, having a report on all protocols, as well as the data size, the payload size. So here we're running again a fourth test with a text file containing only one IP address, but with -n specified, meaning that the host names will not be resolved from the IP addresses within the text file. And this is at normal speed, and you can see that the output is a lot faster. Here we're again reaching Baidu.com. Some interesting observations are that when specifying the data size, there is no effect on the latency. We have no difference with different data sizes, though by default the ones that we've been testing today all have data sizes of 0. Now testing, we also found that specifying an ICMP response wait time did not yield results that were that interesting, because usually the response was well within the limit set. Thank you for listening to our presentation. This was a fun project to work on throughout the computer networking course. It was very valuable to complement the teachings of the class throughout the semester. Again, thank you. This project has been completed and presented by Raymon, Ganaa, and Nick.